Hi everyone, and welcome to Eric's Electronics Workbench. So if you follow this channel, you know I've recently been troubleshooting this military radio, an RT-834, which is a transceiver and it's meant to be used along with the AM3349 RF power amplifier, which then forms the GRC-106A HF radio set. So it operates between 2 and 30 megahertz. Now this RT-834 is an absolute electromechanical wonder of a radio. So it contains a motor, gear trains, a rotating turret assembly in the RF module, relays, vacuum tubes, transistorized circuitry, and even some early digital integrated circuits. So this radio was manufactured under a late 1960s contract date. Now in the part 1 video, I showed that both the transmit and receive frequencies were out of spec, quite a ways off in some cases, but that turning the 100 Hz tuning control to certain positions would help the radio sort of lock in and become closer in frequency. But it was never spot on frequency, but again, in some cases it was pretty close. So I started looking at the 100 Hz tuning module, but I couldn't find anything wrong with it. It seemed to be working perfectly fine. And then I noticed that the 1 kilohertz pulse coming into that module seemed to be way out of spec. So tracking back and seeing where that signal came from led me to the frequency dividers module. All right, so this is the frequency dividers module, and those two circuit boards make up the 100 Hz module. Now, as you saw in the part 1 video, I removed these two circuit boards from the little case they're normally mounted in, just so I could test them. And they're sitting on this notepad so they don't short circuit against the chassis. Now, as you also saw in the part 1 video, the 100 Hz module works perfectly fine when I send it a known good 1 kilohertz pulse from my function generator, but it completely falls apart and its PLL won't lock when the signals originate from within the radio. So the PLL is completely contained within this module. It doesn't rely on any external modules or other components. The phase lock loop happens right on this module, and it's very, very stable when the 1 kilohertz pulse is coming from my function generator, but again, when all the signals are just originating inside the radio, it's completely unstable and won't lock at all. So we know that this 100 Hz module is working fine. There's no problems with it. So I thought I should step back to the next stage and start to troubleshoot at that point. So that brings us to this frequency dividers module and the 1 kilohertz divider. So what I'm doing is I want the 1 kilohertz pulse to come from here and go up to the module, but the input to the 1 kilohertz divider is a 10 kilohertz pulse. And that's what we're testing here, is does this section, the 1 kilohertz divider, work the way it's supposed to? So I'll explain what all these test leads are. So again, this module has to be powered by 20 volts. So that's this test lead right here. It's going over to a 20 volt distribution point on the chassis. This other green test lead is just a ground connection. It's clipped onto the frame of that module. The frame and everything is just a common ground. It comes over here to ground point on the radio. This test lead right here is coming from my function generator. It's bringing the 10 kilohertz pulse into this module. I tagged on a little piece of wire right here just to give myself some more room. The ground on the function generator is clipped onto the module right there. And so the function generator is set to the pulse mode, but it's 10 kilohertz. 1 volt peak to peak, and the duty cycle is just 0.5%. So a very rapid pulse. Now this red wire right here is the 1 kilohertz output. So it's clipped on this component. This is the capacitor, although it looks like a resistor. In a moment I'll zoom you in a little bit closer and you can see the circuit, but this is on the output side of that capacitor. I was already showing you on the schematic, and it's bringing the 1 kilohertz pulse up to the 100 Hertz module. And because I'm not using a coax, I can't plug into these connectors on the input side. These are looped through, so both of these are electrically connected together. But I'm just connected to a capacitor on this module, which is electrically the same as the center conductor on this connector. And then this is the oscilloscope probe right here, and its ground connection. Now over on the module, 100 Hertz module right here, this connector is plugged together, so this is bringing power up to this module, 20 volts. And it's also making the connection to the 100 Hertz tuning switch on the front panel. So there's a binary code that's being brought up here which programs this logic circuit. Here's a closer view on the frequency dividers module. So this is again the 1 kilohertz divider section. So we have the 20 volts DC being brought in on this connection, the 10 kilohertz pulse on this connection right here. I removed this wire right there. This normally ties to this post, and I didn't want to backfeed this 10 kilohertz pulse into other parts of the circuit, so I just disconnected that for now. And then the output, you can see it over here. This is a capacitor, even though it does look like a resistor. This is on the output side of that capacitor. So let me get you moved up to the oscilloscope, and you can see the result. So we have a very stable square wave within the 100 hertz module. So this shows that the 100 hertz module's PLL is in fact locked, because if it wasn't locked, this would be very jittery and jumping all over the place. We already saw that in the part 1 video. So when the PLL locks, then it's stable, just as you see here. And if I turn the 100 hertz tuning control in the front panel, which is set to 0 right now, I'll just step it through. There's 1, 2, 3, 4, 5, 6, 7, 8, 9. Perfect. That's exactly what it's supposed to do. No problems. So I'm going to turn that all the way back down to 0. And then if I turn off the radio, put it into standby, it shuts that module's power off. Then I'll turn it back on. No problems. Locks right in. So all things that we saw in the part 1 video when it would become very unstable and it couldn't relock, so forth. So none of that's happening. Looks perfectly fine. So now I'm thinking on the frequency dividers module that the 10 kilohertz pulse that's coming in, right now that's originating on my function generator, is there something wrong with that input to the 1 kilohertz divider section that would be causing it to become unstable? So I thought, what if I simulate and put in a frequency that's out of spec? Instead of 10 kilohertz, let's lower it down or maybe raise it up, try one of those and see what happens. So I'm going to do that right now. So I'm going to reach up here and I'm going to start lowering the frequency. Move this over. So there's 9.9 kilohertz. And in fact, you can see the frequency does change, but it remains locked. Go down to 9.8. 9.7. Now the PLL is unlocked. So it's basically out of the range of that PLL. Now if I turn the front panel 100 hertz tuning control, it did, yep, there it relocked. That does look similar to what we were seeing in the part 1 video, where it was able to lock at times, but was very unstable. See, now when I go back down to 0, it remains locked. Kind of, it's jumping around, it's not entirely locked, but kind of wants to lock in. If I go down a little bit lower in frequency, loses it again. That's 9.6 kilohertz. Okay, there it locked again. I'm turning the 100 hertz tuning control on the front panel. Unlocked it, couldn't keep it there. So that's kind of similar to what we saw in part 1. And definitely the way that looks right there, that's absolutely the same as originally what we saw in part 1 when I was starting the troubleshooting and taking the initial measurements. So I'm wondering if the frequency is out of spec and in this frequency dividers module, or even working back further towards the time base if there's a problem. Now, also in part 1, I checked the main 5 megahertz output and it was spot on. I didn't see any problems there. But something maybe is out of spec or has drifted. So I'm going to go back up here, 8, 9, and then there's 10 kilohertz. Let's just go up in frequency. Stepping up higher in frequency. That's 10.9 kilohertz. It starts to lose there. Yeah, there. Okay, there's 11.3 kilohertz. It's way off. Turning the tuning control. Yeah, it does lock. Tries to lock. Not really. That's stable. Go back down again. Yeah. So if the frequency goes too high or too low, it just gets out of the range of the PLL. Okay, that's back to 10 kilohertz again. So, just kind of thinking of some ideas of where the problem might be, but I think we need to go back yet even further to that 10 kilohertz stage within the frequency divider. All right, so now I want to check the 10 kilohertz pulse in the frequency dividers module. And the 10 kilohertz pulse is what goes into the 1 kilohertz divider section, also in the frequency dividers module. That's the part of the circuit we were just testing. So to do this check, I've reinstalled the frequency dividers module in the radio. It looks different than these other modules because it doesn't have the top cover installed on it. And I have this wire tacked onto a test point in the module that's called out in the service manual as the location to check that 10 kilohertz pulse. And then this is going up to the oscilloscope, and I'll move you up to the scope in just a moment and you can see the waveform. Now that this module is back in the radio, it's powered up, the radio is creating all its own signals, so I'm not injecting any signals into the radio at this point. It's all self-contained, and I've already checked the phase lock loop in the 100 Hertz module, and it's unlocked. So the 100 Hertz module seems to be testing okay. The 1 kilohertz divider seemed to be testing okay in here, and that 1 kilohertz divider is of course what sends the signal over to the 100 Hertz module. So individually these circuits seem to be working, but you put them all together in the radio and they don't cooperate and things fall apart. And I did test the coax that goes between this module and the 100 Hertz module. There's no short circuits, nothing looks suspicious on the connectors or the coax or anything like that. So if we take a look at the schematic right here, it's touched up. I'm checking the 10 kilohertz pulse right at this point. So there's a capacitor right there. We're on this side of the capacitor. And then right here there's a note in the service manual. So if you were making an adjustment on this frequency dividers module in the 10 kilohertz divider section, it says here that the waveform should be a pulse with a PRR, which is pulse repetition rate of 100 microseconds, a pulse width of 9 microseconds at 50% amplitude, and an amplitude of approximately 8 volts peak to peak. Well, let me move you up to the oscilloscope and take a look at the results. So here's the 10 kilohertz divider's waveform, and it looks great. So check out the measurements. Frequency 10 kilohertz, peak to peak voltage 8.6 volts, pulse width 9.9 microseconds. Essentially you could round that off to 10 microseconds. So those numbers are exactly the same, if not very, very close to what's given in the service manual. It says that the pulse PRR, or pulse repetition rate, is supposed to be 100 microseconds. That's easily seen if just go like this. So now the horizontal scale is 50 microseconds per division. We have 2 divisions, so it's spot on for the 100 microseconds. This is a pulse width of 9 microseconds at 50% amplitude, and it's reading very close to that. Let's go back over here. So it says 9.9 microseconds. So a little bit wider pulse, almost by a full microsecond. Is that a problem? I don't think so, but we'll keep that in mind for the troubleshooting. That pulse width maybe is just a little wider than would be ideal. And then it says the amplitude is supposed to be 8 volts peak to peak, and of course we have that. There's very, very close to that value, just a touch over. So I was looking at these measurements and thinking, you know, it doesn't work in the radio when everything's put together. What's different from being in the radio versus when I'm testing it? And then suddenly something really stood out. When I was testing the 1 kilohertz divider section, I was using a much lower amplitude on the 10 kilohertz pulse. I was using 1 volt peak to peak. Now the way that I came up with that value is that I didn't know exactly how high the amplitude was supposed to be. I hadn't read this part of the service manual that mentions the 8 volts peak to peak. So I just started at a very low value, down in the millivolt range, and I was increasing it until the circuit started to work. And it locked in and started functioning around, I think, 800 millivolts, 900 millivolts, right around there. So I just nudged it up to 1 volt and called it good. It seemed to work perfectly fine. Well, obviously it's supposed to be a much larger amplitude. So that's a big difference from how I was testing it to, you know, how it actually is working in the radio, or what the signal is being supplied to the 1 kilohertz divider in the radio. So what I need to do is replicate this signal that we're seeing on the oscilloscope with my function generator and test the frequency divider module again away from the radio and see if it fails by using the higher amplitude signal, because that's a big difference in how I was testing it. And then if it does fail, it would point to a problem in the 1 kilohertz divider. So we'll definitely try that. And I'll keep in mind the pulse width on the value that's given, 9 microseconds, although they do say at 50% amplitude. I'm not sure on this oscilloscope it says the pulse width 9.9 microseconds. It's a change there, but you know, the waveform is basically parallel on each side, so whether the pulse width was measured here or up here, I think it would basically be the same. About like that. You can see, I mean, the sides are parallel. Now let me move the oscilloscope over to the PLL in the 100 Hertz module, and you'll see that it's unlocked, even though this signal looks perfectly fine. And let me get this over here. I've got to reach around the other side of the camera to get to this probe right here, get that. Have to clip the ground lead back onto this module. Okay, I think that's making the contact there. Oh, there we go. And just adjust this. So you can see the PLL is unlocked in that 100 Hertz module. And we've seen this waveform before, certainly in the part 1 video I was showing this. Now I'm going to turn the 100 Hertz tuning control. It's at 0 and I'm going to start increasing it. Oh, slow this down again here. So you can see now it has locked in. I mean, you would say, well, that seems to be okay. But I actually noticed something else, and I'm turning it right now, and you can see how it's locked in. And then that's back to 0 again. You know, now it's locked, and we saw that in part 1, where if you can get it to lock, sometimes it will stay locked in. But take a look at the frequency up here. 833 hertz, 833.34 hertz. That frequency is wrong. And I didn't notice that before. I thought that was running at 1 kilohertz, even though it was unlocked. But that's definitely incorrect. And that frequency would be coming from the 1 kilohertz divider, because the 1 kilohertz divider is sending the signal over to the 100 hertz module, and that 1 kilohertz, or what should be 1 kilohertz signal, and that pulse, is the reference on the PLL. So the PLL is going to try to lock to that frequency. So it must mean that the 1 kilohertz divider right now is running at 833 hertz, which is, it's way too low. It's supposed to be 1 kilohertz. So definitely, it looks like an issue going on with that 1 kilohertz divider. We've got to go back and look at that part of the circuit and see what's going on there. All right, so I'm back to checking the 1 kilohertz divider section. So like before, I'm injecting a 10 kilohertz pulse into the circuit, tacked on this short piece of wire to a terminal on the board, and normally this other wire right here that comes from the other side of the module would connect to that terminal. This is the wire that brings the 10 kilohertz pulse into the circuit, and that's the 10 kilohertz pulse that we just measured. So with the measured values of that 10 kilohertz pulse, I'm duplicating that with my function generator. So I have the function generator in the pulse mode, 10 kilohertz, 8.61 volts for the amplitude, and the pulse width of 9.95 microseconds. So again, those are the same parameters that we measured on the oscilloscope. So this is duplicating that signal exactly for what the module would normally be doing. Now this is just bringing 20 volts DC into the module to power it up, and this is off to the oscilloscope to monitor the output. Now I started measuring around the module, taking some DC voltage measurements, checking capacitors and resistors, and looking at various signals with the oscilloscope. And everything looks really good, as before, where this is working outside away from the radio, but again, when it's in the radio, everything falls to pieces. Now, the first thing that I started doing was adjusting this pulse right here and kind of seeing how the amplitude and the pulse width would affect the operation, and it turns out that this circuit is very forgiving on the amplitude going in and the pulse width. So it doesn't seem to be very critical on what those values are. So I don't think that's a problem. I had already mentioned that the 10 kilohertz value that we measured that's coming from the module itself had a pulse width that was slightly different, about 1 microsecond, different in what was mentioned in the service manual. There's no way that that would be a problem because, again, changing that value on the function generator didn't cause any problems in the circuit, so I'm not worried about that. So then I started looking around the circuit, sort of just by chance. I ended up touching this transistor. So you can see there's 2 transistors here, and they're a metal can style transistor, and I ended up touching it, and that can is electrically connected to the collector of the transistor. And when I touched it, just kind of bumped it by chance, the signal jumped and it went to the wrong frequency. In fact, it went to that same 833 hertz frequency that we saw when the module was in the radio. I thought, whoa, there it is. It's not working. So again, just touching this, now not pressing on it. I wasn't actually, putting any force. It was just a light bump. And so I kind of started touching components in this area and looking around. And if I take an insulated tool like this and come in here and touch things and actually start pressing on components, it doesn't have any effect. It has to be, an electrical connection. By me touching it, basically I'm acting like an antenna and injecting noise into the circuit. And it turns out that bringing my finger close to some capacitors around here really has the same effect, But oddly, touching the input like this also has the same effect. And right now I'm looking up at the scope and it's 833.35 hertz. So I'll move you up to the scope here in just a second. You can see the result. But that's that same frequency that we saw where this was not running, correctly in the radio. Now in the radio, nothing's touching these components. So I started thinking, this is really unusual. Why would it be doing that? Now there's an adjustment right here. I hadn't touched this adjustment. And I looked in the service manual and it says that this adjustment, to make the setting, you would turn the adjustment all the way to an extreme end. I think it's fully clockwise. I'm not sure, I'd have to look again, but I think it's fully clockwise. But whichever extreme end of the range is that they want you to go to, then you start adjusting it back the other way until the divider circuit locks. And then you continue to adjust it until it unlocks, and you count the number of turns and set this halfway between. So a very easy adjustment to make, and I can certainly try to do that. But what I noticed is, if I take this adjustment tool right here and just get this, okay, right there. So I don't know if you can see kind of a reference, the markings are right there, but I'm looking at the top, the little screwdriver end right there, and I'm watching up on the oscilloscope. Again, I'll show you this on the scope in just a moment. But if I turn this right there, it just unlocked and it went to 833.34 hertz. So this top right here was horizontal this direction, and now it's just slightly angled up. So if I turn it back right there, it locked again. So there's no way that that adjustment is halfway in the range of its travel if just turning it that much back and forth. Kind of see just that slight rotation I'm giving it. I'm looking at the scope and it's going between locked and unlocked, or essentially, the correct frequency and then the incorrect frequency. So I think maybe the adjustment is the problem. So I need to try and readjust that, and I'll put it what should be in the middle of the range based on the instructions, and then let's see if things improve here. I don't like making adjustments if there's a problem with a component, because essentially, it's trying to mask the problem, and if the defective component is still in the circuit, in the long term, it probably won't keep working correctly. So I want to make sure that there aren't any defective components or other problems in the circuit. But so far, everything else is checking out okay. All the pulses, all the signals look excellent through the circuit, but it's like it's on the ragged edge of not working correctly, and this adjustment seems to be having a big effect on that. And once I turn this adjustment and it locks in, then touching the transistor no longer has the effect of making the circuit go to the wrong frequency. So it seems very stable. Right now it's, again, right on that ragged edge of instability, and just coming in here and touching things seems to upset the circuit. So let me move you up to the oscilloscope and you can just see the result here. So this is the output right now, and everything looks perfect. You can see the frequency is right on 1 kilohertz. So I'm going to touch the input from my function generator, and there it goes, 833.34 hertz. So that's obviously not right. And then it goes back when I take my finger off of the test lead. I'm going to touch that transistor right there. You can see how it's incorrect. Goes back again. I'm going to just very lightly touch that capacitor, and you can see it's incorrect. Take my finger away, it goes back again. And again, I'm not really pressing on any components or flexing anything in any way, and touching with an insulated tool doesn't have the effect. It has to be basically like me acting as an antenna and sort of putting noise and interference into the circuit, which then seems to upset it. So now I'm going to go down here and turn that adjustment. Okay, so I put the tool on there, so turning the adjustment just a little bit. There it goes, unlocked. Rotate it back just a little bit, and there it locks. Go just a little bit off, unlocked, wrong frequency, and back again. So I'm going to try and make the adjustment. Let's see what happens. All right, so I'm going to try the adjustment on the 1 kilohertz divider. So this 1 kilohertz divider actually has two main parts to its circuit. The input goes into a bistable multivibrator. That takes the 10 kilohertz and divides it down to 5 kilohertz. Then the 5 kilohertz goes into an astable multivibrator. That's where this adjustment is located. And the output from that stage is the 1 kilohertz pulse. So the instructions say to make the adjustment, you turn the trimmer pot fully clockwise, and when it hits that extreme range, then start going counterclockwise until you go into the 1 kilohertz range. And then when you hit the 1 kilohertz range, count the number of turns it takes to leave that range. And when you leave the range, go back halfway. So I'll count the number of turns, I'll let you know where I'm at. Now I already showed you how sensitive the adjustment was, and it took just a little bit of a turn counterclockwise to leave the 1 kilohertz range. So I'll do that right now. I haven't adjusted it. This is where it was, for the starting point. And you watch the oscilloscope, if I just go a little bit right there, it leaves the 1 kilohertz range, and basically it's going down to the next range. That's at 833 hertz that we've been seeing. So that took very little movement of that trimmer pot to leave the 1 kilohertz range. So there's no way it could be centered up. I just turned it back to where it was there. But yeah, I think the adjustment is the problem. It seems to be skewed way over to one edge of the 1 kilohertz range. But let's find out here. I'm going to start turning it clockwise. So here we go. Turning it. Oh yeah, there's multiple turns here, and it's still in that range. Up there, just left. Yeah, so it is way out of adjustment. I think that's the problem. So still turning. Oh, there's another range. Still turning it. Oh, there's another range. Another range. I'm still turning it. Okay, that's 5 kilohertz. So it's got to be close to the edge of the extreme range because 5 kilohertz is the input signal. Okay, so now I'm going to start going counterclockwise. Turning it here. Still turning it. Still turning here. We should be pretty close. Okay, there it goes. I want to make sure I'm right at that edge. Okay, there we go. Right there. Okay, perfect. Now start to count the number of turns here. So we'll go 1 turn, 2 turns, 3 turns, 4 turns. Oh, okay, it just left it there. Go back again. Yeah, okay, 4 turns. So now let's go 2 turns back. So we'll go 1, 2. Okay. That should be the correct setting. Let's see what happens. I'm going to touch the test lead going in. Hey, look at that. It's not affected anymore when I touch the test lead coming from the function generator. And let me reach over to the transistor. Oh, outstanding. It's not affected when I'm touching those components. The circuit seems very stable now. Oh, this is looking very good. Perfect. How cool is that? So I'm just touching the same areas, those capacitors and the transistor. Yeah, it's very stable. Perfect. Excellent. Yeah, that was way out of adjustment. So I thought it would be a good idea to check the other divider adjustments in the frequency dividers module. So there's a total of 3 adjustments. This one that I already made that was way out of spec, this adjustment, and then one on the other side of the module. And these other 2 adjustments weren't that far off, but at least now I know that all 3 adjustments are spot on. So now I'm testing the complete division chain in the module. So I'm inputting a 500 kilohertz sine wave, and normally this signal comes from the frequency standard module. So the module's powered up, it's connected to the oscilloscope probe right here. So this is on the output from the 1 kilohertz pulse. And I reconnected the wire that was desoldered for testing. It was right in this area here. So now check it out. Move you up to the oscilloscope. Looks great. So there's the 1 kilohertz pulses. So again, the module is dividing down the 500 kilohertz input signal down to this 1 kilohertz pulse. And yeah, it looks great. No problems. They're very stable. And if I touch the transistors, right now I'm touching those, and the capacitors, where it was very unstable before, it's rock solid. No interference, no problems. So I think the module is ready to put back into the radio. Alright, so the frequency dividers module is back in the radio is powered up, and now there are two things that I need to check on the 100 Hz module to make sure that everything's working correctly. First of all, I'm checking if the PLL is locked, because that's been a big problem all along, is that when the frequency dividers module is in the radio and everything's connected back together, that the PLL becomes unlocked in this 100 Hz module. So the good news is that it is locked now, and I'll move you up to the scope in just a second. You can see the result. And I'm also making sure that the waveform looks correct at this test point based on the information that's in the service manual. And I did need to touch it up just a little bit. I've already done that. You can see the result on the scope here in just a second. The adjustment is right here on this other board there. And then the other thing that I needed to check is if the output from the decade divider is correct and if the frequency moves through the proper steps in the proper range as I turn the 100 Hz tuning switch on the front panel. So let me move you up to the oscilloscope here. And just get this touched up a little bit so you can see the display a little easier. Alright, so that waveform looks excellent. It's right in spec. Take a look at this pulse width right here. So it's 599.4 to 0.7, and it jumps around just because of the effects of the oscilloscope and the triggering and so forth, but it's very, very good. I've also checked this pulse width on the frequency counter, and it's actually more stable on the frequency counter. So this pulse width is supposed to be 600 microseconds, and that's the width across like this, and it is. So this is 200 microseconds per division, so 2, 4, 6, and of course that's how the measurement is reading right there. And this portion of the waveform over here is supposed to be 400 microseconds, and it is, because we have two divisions, so it's spot on. And I already made the adjustment. It was off by just a little bit, and I just touched it up and it dialed right in. So this is really as close as I can make it. If I turn the adjustment any further, then this sort of jumps up a little bit further than I'd want, so it's perfect. It's running about 599 microseconds. And it's very stable, no problems. If I turn the 100 Hz switch for tuning here, see how it adjusts now? So you go through all the steps, and that's how it's supposed to do it. No problems there. Looks good. And this adjustment, when you check the pulse width for 600 microseconds and 400 microseconds, that's done when the 100 Hz tuning switch is at 0. All right, so everything looks very good there. Also, the frequency is correct, 1 kilohertz. It hasn't shifted off to a different frequency now. So very stable. So all good news on that. Let me move you up to the frequency counter here. And I just need to move this over right here. Do this. So, and I'm going to move the probe over to the decade divider. Should be good to go there. Alright, so now it's at the 0 for the tuning on the switch, and that's supposed to be 11 kilohertz, and it should go in 100 hertz steps now. So I'll go to 1 or 100 hertz, and yes, there it is, 11.1, 11.2, 11.3, 11.4, 11.5, and right now it's at 500 hertz on the tuning, so it is tracking correctly. 0.6, 7, 0.8, and final step, 0.9. Perfect. Excellent. So I think the radio is basically working the way it's supposed to now. I'm not seeing any problems. So what I need to do is get the 100 Hertz module put back into its case, put things back together in the radio, and let's connect the radio back over to the HP-8920A communications test set. And let's check the frequency for the transmit, and I'll give it a signal in for the receive, and let's see if it's performing the way it's supposed to. Alright, so the 100 Hertz module is together and back in the radio. So the radio is assembled the way that it's supposed to be, other than it's just not in its outer case. So let's see if the RT-834's receive and transmit frequency problems have been taken care of. So the radio is powered up. It's been warming up for about a half an hour now. I have the speaker connected. You can see that sitting over here. And I have the microphone connected, so it's ready to go when I do the transmit test. We'll start with the receive test. So I have a coax connected. This is bringing a signal into the radio. So it says receiver in. This is the antenna connection on this BNC connector. There's also a terminal right here for a long wire antenna. And then when I do the transmit test, I'll just move this coax over to this BNC connector. This is RF output. So this coax is going over to my HP-8920A RF communications test set. So the 8920A is acting like an RF signal generator, and it's set to the same frequency that I have dialed in on the radio. So this is at 3.0500 megahertz. And the first thing that I want to check is the radio receiving at the displayed frequency? And an easy way to do that on this radio is to put an unmodulated carrier into the radio and then listen for a beat frequency when the carrier is at the same frequency as the displayed frequency. You shouldn't hear a beat frequency, and that's exactly the case. So if I get closer to the speaker, you might hear kind of a rushing sound. There's also some fan noise from the power supply. There's definitely no tone, there's no beat frequency. Now, if I tune down in frequency, then you should hear the beat frequency. But again, this is unmodulated. So what I'll do is I'll turn this down to 4, bring this up. Okay, there you go. And then if I turn the 100 hertz control all the way to 9, so now 499 is very close to the 5 that we were at. So the beat frequency has essentially disappeared. The microphone may not be picking it up. There's a tiny, very low level, very low frequency. I would describe it almost like a little bit of a rumble is all. I mean, it's basically completely gone. There's no tone. But if I go like this, you can hear that now. It starts to pick up a little more, perhaps. Let me turn the volume up there. Easily hear that. So I'm getting further away as I'm tuning down in frequency. And you can hear how the tone is changing. If you go farther off, it gets very high in frequency, and to the point that you don't hear it anymore. So perfect, that's the way that's supposed to work. So let me go back down here. Okay, so that's back to the same frequency, and this is just a random frequency I picked. This would work on any frequency that the radio can tune to. But now I'm going to turn on the modulation. So the signal generator will be set to the same frequency, but I will modulate it, so it's AM modulation, and I'll do 50% modulation with a 1 kilohertz tone, and we should now hear that tone in the speaker. So we'll reach over here and turn that on right there. Perfect. Probably hear that. So 1 kilohertz tone. Excellent. And of course, if you tune down in frequency again, you would get the beat frequency mixed in with that tone. Now, in the part 1 video, when I was first testing the radio, there was definitely a lot of beat frequencies going on, and it was all over the place on the received frequency. And I really couldn't find any place where it would be silent and tuned correctly. So, it was all over the place on the frequency, really drifting around and not stable at all. But this is perfect. This is right on frequency, and it's working the way that it's supposed to. So very happy with how it's receiving. So let's try the transmit test. I'll move this over, and I'll move you over to the HP-8920A because for the transmit test, you'll want to see the results on that display. All right, let's see how the RT-834 is performing on transmit. So I have this set to the auto tune mode, so whatever the carrier frequency is, this will automatically lock on. Now, the numbers are meaningless because I'm not transmitting right now. And it's set to the AM demodulation. So when I talk into the microphone, this will demodulate that audio. If I increase the volume, then you'll hear my voice on the internal speaker if everything is working correctly. And keep in mind that this is acting like a dummy load, so there's absolutely no radiated RF power when I'm doing this test. That's always important when you're testing a transmitter. You never want to cause interference to authorized users on a frequency. And even if the radio is very low powered, as the case with this radio, the output power is down in the milliwatt range, but you still don't want to be radiating out on an antenna or something like that. It needs to be tested into a dummy load. All right, so here we go. I'm going to key the microphone. The radio is still set to 3.0500 megahertz. Let's see what happens. Hey, look at that. Perfect. So 3.0500, and there's an extra 0 of accuracy. Outstanding. So if I talk into the microphone, oh yeah, there it goes. You can see the percent modulation. Looks very good there as I'm talking. So if I reach over here and increase the volume, it should hear my voice, and yes, it does, no problems there. So it's almost, it's a little bit of feedback there. So yeah, it does pick up my voice okay. Yeah, very good. You can hear it probably beyond my regular voice, kind of in the background maybe a little bit there with the microphone. So the microphone's close to me right now, but it is definitely demodulating. I'll turn it back off again. So yeah, the radio is clearly modulating the carrier properly and very, very accurate. So that's far more accurate than it was in the part 1 video when I was initially doing the testing. And I had mentioned that I thought the transmitter frequency was somewhat accurate, but maybe off a little bit. And it was pretty close, but this is far more accurate. This looks very, very good. So I'm going to change the frequency. Let's just try something else. We'll do a small increase. Let's just go to 1. So it's 3.0510. 3.0510. Outstanding. Let's try going with the 100 hertz control. I'll go to 2. So 3.0512. 3.0512 and an extra 0 after it. How cool is that? Very, very accurate. Very happy with that result. So let's go like this. I'll go down, just change this to something else that's kind of random here. So that's the motor doing the tuning. And I'll just pick something else here kind of at random. So I have it at 12.1020. So just a random frequency. Let's see what happens. 12.1020. Perfect. Outstanding. Very, very accurate. And again, if I increase the volume here. So yes, you can hear in the background, it is demodulating it. So it means that the radio is modulating the carrier with no troubles. So very happy with those results. I think this radio is now working the way that it's supposed to. Now in the part 1 video, I had mentioned that there were some test points on several modules that seemed to be loose. Probably just a broken solder, but I'm not really sure exactly what kind of damage they have. They need to be looked at because you can't make accurate measurements at those test points when they're wiggling around and making a poor connection themselves. So the next thing that I'm going to do is pull those modules out, disassemble the modules, and see what's actually damaged. Again, I think it's probably just a broken solder on the circuit board. Hopefully the board itself isn't broken in some way. I think what happened was a probe was in those test sockets and it got pulled kind of hard and ended up breaking something. So let's find out what's going on with those test points. I'll pull the modules out, I'll take it apart, and I'll show you what I find out. Here's the megahertz synthesizer module, and I removed its cover. And check out the stack of rotary switches. So all these wafers in here, a bunch of crystals, capacitors. So there's a mechanical coupling, and of course the electrical connector. Turn around here, you can see their side. Just amazing electromechanical construction in this radio. So the DC lock test point is right over here. It's this test point right here. And it seems to be loose when I move it back and forth on the board. It just doesn't feel quite right. So what I want to do is remove this board, sort of just tip it up a little bit. There are quite a few wires and coax cables that attach to it. I don't want to desolder all of that if possible. So I'll just remove the screws, and if I can just lift it up enough to get underneath the board and check the solders on that test point. So I'll try to do that. I was able to get the circuit board to tip out just a little bit, so now I have access to the back of the board. But unfortunately nothing can be done to fix this. Look down in here with the light. You can see there's a pad on the board right there that has lifted. That's the test socket. It has a lead on each end of the socket, and this pad doesn't go anywhere, and it was very small, so it's not a surprise that it would break away from the board. But I think this socket has been replaced at some point because the other side is the trace that goes into the circuit. It has a lot of flux around it, so I'm going to clean that up. But on this side, really nothing can be done to repair that pad. So at least the other side is making electrical connection. So we'll just have to be very careful of this test socket if it has to actually be used. So I was able to improve things just a little bit. I noticed a visible gap between the pad and the board, so it's bad enough that the pad's broken off of the board, but that extra space gave some wiggle room to let the socket move up and down and kind of shift around on this end. So what I did is I supported the socket and the board on this side, came in with my soldering iron, heated the connection, and then I used a screwdriver, and while I was heating it, I pressed the pad that direction against the board, essentially sandwiched everything together, kind of squeezed the pad and the socket down to the circuit board. So now it has a very secure feel, and on this end the socket isn't able to wiggle around even though that pad is still broken from the board. It doesn't have that gap anymore. So I think that socket has definitely been replaced because it looks like someone was kind of struggling with that soldering and overheated the pad and ended up, lifting it off of the board. And this circuit board has a conformal coating on it. It's a real nuisance when boards have conformal coatings. It can really cause problems with desoldering, and I think this just got overheated. That's why that lifted. So I cleaned up the excess residue, kind of the old conformal coating that had melted, and there was some flux as well. That's all been cleaned up, so it looks good on the other side, and at least the electrical connection on the other side of the socket, that's what really counts. That looks perfectly fine. There's no problem with that trace. So if the socket has to be used in the future, I'll just be careful with it. Let's take a look at the test sockets on the frequency standard module. So I've already removed the module's cover right here. So taking a look at these test points at the top, it seems like this socket right here is quite loose. So the plastic can move around the actual contact in the center, and that's normal. But if we look like here, you can see it looks like the lead that comes off of that socket and goes down in the circuit board is also moving right there. I think this socket, yeah, that's quite loose. See how that rocks around like that? And then on the other side here, yeah, you can see that's very loose right there. It's quite loose as well. You can see how the lead that comes off the socket right there is wiggling around. That one seems okay. This one is, again, the plastic can wiggle around the socket itself, but the actual lead going into the circuit board on this one seems to be firm. So 4 of the sockets look like they need some attention. Now hopefully the pad isn't broken on the back side of the board, so we'll have to find out what's going on here. It looks to me like to remove this board, there's a wire that goes through the board right here. I'll get you zoomed in a little closer so you can see. This point right here has a wire that attaches to it, and that passes through to the circuit board. You can see right here. So if I desolder that on one side, then it'll allow both boards to kind of lift up and out because these coaxes and other wires look like there's enough room. So I can tip the board out and then be able to look at the back side. And this area over here is the ovenized crystal oscillator. Turn this around, you can see on the bottom right there. The sockets that plug into the chassis. All right, so let me work on these circuit boards and I'll show you what I find out. So I got lucky on both of these circuit boards. It's just a cracked solder on each of the test sockets. So if we look at this one on the corner, you can see if I wiggle it around, how that lead is moving, but the pad is not lifted from the circuit board. See how it's moving right there? So again, no damage to either of the circuit boards. And it looks like the solder on these connections for the sockets is very sparse. There's almost no solder there in the first place. Same thing on this one over here, and also on these over here. Now the components on the boards look to be soldered perfectly fine. I don't see any issues there, so I'm not sure why these sockets didn't receive all that much solder, but it's no surprise that they would crack. If a test lead was poked in and it was pulled to the side just a little bit, it wouldn't take much force to crack one of those solder joints. So I'll just go through and resolder all these sockets and we'll be good to go.
Broadcasting on internationally allocated
So the station that you just heard there, which you could probably hear by the identification, is WWV out of Colorado. And that station operates on 2.5, 5, 10, 15, and 20 megahertz. This is set to 20 megahertz. So it's receiving very well. I have just a very simple antenna connected right now. So it's not even an outdoor antenna, it's just here in the shop for this test, and it's able to receive that 20 megahertz broadcast. If you hear a female voice, that's out of Hawaii. That's the sister station WWVH. That station operates on 2.5, 10, and 15 megahertz. So the different frequencies are used so that you can tell the band conditions, because atmospheric skip changes depending on the frequency and the time of day, other conditions. So again, you can tell a lot about reception type conditions and what's going on by the different time stations and which frequencies you can hear them on. So it's daytime right now, late afternoon, and this is receiving very well on 20 megahertz. So I'm adjusting the frequency standard in the radio. I haven't actually adjusted it yet, but I'm going to. I'm letting the radio warm up. It's been on for about 15 minutes right now. So the module sits over in this corner, and I took this top cover off right here, this little plate, because I can't get my tuning tool to reach down inside the module with that cover on there. And the ovenized crystal oscillator is right here. So that's the frequency standard module that I was just repairing, those broken solder connections on those test points. So let me get you zoomed in here, and I'll just move it up to the frequency counter, and you can see where it is right now. Again, I haven't actually made any adjustments yet. So it's supposed to be at 5 megahertz, and it's very close to that value, but I'm going to try to adjust it a little bit closer, but I want to give the radio plenty of time to warm up and stabilize first. So the radio's been powered on for over an hour now, so the ovenized crystal oscillator's had a chance to warm up and stabilize. I made a minor adjustment to it. You can see the result. It's spot on 5 megahertz, so very happy with that result. And that frequency counter has an ovenized crystal oscillator, and it's been calibrated against my GPS discipline oscillator, so that frequency counter is known to be very, very accurate. So I'm certain that this radio will now be spot on frequency when transmitting and receiving. So this wraps up the troubleshooting and repairs on the RT-834. Looking back, the solution to the problem seemed simple. It was just an adjustment that was way out of spec. But when you start the troubleshooting, how do you know that? You would never just go into the radio and start turning adjustments, hoping that it somehow fixes things and makes the radio work again. If you did that, it would throw the radio way out of calibration and make a complete mess of it. So I hope you enjoyed this troubleshooting adventure, going through several modules, looking at various signals, testing various circuits. And if you did enjoy this video, you can let me know by giving it a thumbs up. And if you're enjoying the content on this channel, don't forget to subscribe. There'll be many more videos coming up in the near future. Lots of projects in the queue, and you won't want to miss any of those. All right, as always, thank you for taking time to watch. And until next time, take care. Goodbye for now.